Hello students. So today we will talk about electrovalent, or you can say ionic bond formation. So yesterday the bond formation that we're talking about, in those bond formation, we were talking about the sharing of electron. Okay, we are talking about the sharing of electron, but in ionic bond there is a complete transfer of electron from one atom to another atom in such a way that both of the atom who are losing and gaining electron gets the noble gas configuration at the same time. So these type of bonds are called as ionic bonds or electrovalent bonds, right? So let us see how does this so first let's see a illustration. How does the atoms lose an electron? We'll take a simple symbolization of a atom. Say we have a atom A. It loses an electron and gains a positive charge. Okay, right? And similarly, if you take B and it gains that electron and it becomes B negative, right? Now A plus and B minus will overall make a neutral molecule, because the molecule that we know, or the molecules that are stable should be a neutral one, right? Now such type of bond is formed when one of the atom can easily lose electron while the other can gain electron, and thus each acquires the stable electronic arrangement of the nearest noble gas. Okay. Now let us take a real example of sodium chloride formation. So this is sodium chloride. So sodium will lose one electron, it will become Na plus. Okay, because 281 is the configuration. After losing one electron, it will have 8 electrons in the outermost or valence shell, and this conforms our octet rule. Similarly, chlorine has 7 electrons in the valence shell, so it will gain that one electron lost by the sodium to obtain the Cl minus configuration, or you can say the noble gas configuration of 288. Now we have Na plus and Cl minus. If you bring both of them together, then these two species combine with one positive and one negative charge to give us NaCl. Okay, so we can have more examples of ionic bond like calcium fluoride, which is CaF2, magnesium oxide MgO, magnesium bromide MgBr2, calcium sulfide, okay, CaS, then sodium sulfide. Now what is electrovalency here? So electrovalency is basically the number of electrons lost or gained during the formation of electrovalence linkage. So this is called as electrovalency. For example, the sodium and calcium loses 1 and 2 electrons. Sodium loses 1 electron and calcium loses 2 electrons. So their valencies are 1 and 2. Similarly, chlorine gains 1 electron and oxygen gains 2 electrons. So they both have electrovalency of 1 and 2 respectively. So valency is basically equal to the charge on the ion that is gained upon transfer of electrons. Now next is coordination number. So the number of moieties that are attached to a single atom is called as what? It is called as coordination number. For example, NaCl, each sodium chloride is surrounded by 6 equally spaced chloride ions. So when you will see the solid structure of sodium chloride, you will observe that they have 6 chlorine minus ion surrounding each Na plus. Similarly, 6 sodium plus ion surrounding each chloride ion, and this leads to a coordination number of 6. Next, the formation of ionic bond involves the formation of positive ions. Okay, so positive ions formation takes place by losing electron. Positive formation of negative ion takes place by gaining electron, and this both positive and negative ion comes together by electrostatic force of attraction, right? Because one is positive, one is negative, both will attract one another. Now in the process of losing electron, the energy that is being supplied is called as ionization energy. So here is the ionization energy. Na goes to Na plus by losing one electron. Similarly, Mg goes to Mg plus by losing one electron. Okay, now since sodium is going to a noble gas configuration, therefore its energy that is required, it is less, whereas in case of magnesium it is more. Next is electron gain enthalpy or electron infinity. So both have the same absolute values, but their definitions and the signs are totally different. Okay, so if I talk about electron gain enthalpy, so suppose I am talking about the electron affinity. So it is the amount of energy released when an extra electron is added to the isolated system. So that is called as electron affinity, and that extra electron is added to the gaseous phase, okay, or gaseous negative ion. Now let us consider the case of, say, oxygen. So first, oxygen will add up one electron to become monovalent ion. So O minus means one negative charge, so therefore monovalent ion, by release of certain amount of energy. So electron affinity for this process is 142 kilojoule per mole. But in the process of oxidation of second electron up to the monovalent ion, energy is required to overcome the force of repulsion. So because it has already a negative charge, you have to add one more electron, then you have to come over to that repulsion between the electron and the negatively charged species to make it O2 minus. So that requires more energy of minus 693 Kelvin. Clear? Next is lattice enthalpy or lattice energy. So whenever 1 mole of lattice is formed, so that is the energy released during the formation of 1 mole of a lattice, then we call it as lattice energy. Clear? Okay. Now the higher the value of lattice energy, the resulting ionic, greater will be the stability, because more energy is released means more stability is gained, means the compound is brought to a lower energy, right? Clear? Suppose the force of attraction is given by Q1 Q2 by D square here. Next is, hence the value of lattice energy depends upon two things. First is charge on the cations. Okay, first is charge on the cation. So more is the charge of cation, more is the force of attraction, and hence more is the stabilization. Okay. Second is the size of the ion. So as highly charged species are rare, okay, the other factor that is defining this is internuclear distance. So if the interdistant nucleus between the ions become more important if the size of the ions is large. So if this internuclear distance is more, that force is small, and that will result in less electrostatic force. So the lattice energy that is released is not that much high in content. But the primary factor is charge. So if the charge is different, we will not move upon the size of the ions. So unless that size is, it is generally not asked to compare the lattice energy between two very abstract molecules. So they are closer in periods or they are closer in groups. In that way it is asked. So if you have to, if it has a differentiation in charge, then you will look upon charges only rather than looking upon size of the cations or size of the ions basically. So what is the net effect here? So lattice energy is one of the effect and electron affinity is one of the effect. Okay, two are the effects here. So if both of the effects have a greater value than the ionization energy, then the net result will be release of energy, and hence the ionic bond is formed. Now most of the ionic bond compounds are formed between cations from metals. Okay, it is formed between cations for metals and anions from non-metals. However, a very common exception is NH4 plus, a cation made from two non-metallic elements. So this is an exception here. Okay, a large number of ionic compounds are known in which NH4 plus ion is a cation. So I was talking about lattice. So this is the lattice I was talking about. So if I talk about the general characteristics of solid, so they exist in this form, rock salt. Suppose I am talking about NaCl. So this is the rock salt form. If you see here, suppose I am taking this one. Okay, I am taking this chloride. This is Na plus ion. So it is surrounded by how many sodium ions? 1, 2, okay, 3, 4, 5, 6. So 1, 2, 3, 4, and 5, 6. So this one and this one, 1, this one and this one, 2, this one and this one is 3. Okay, so 3 pairs are there. Therefore, each chlorine atom is surrounded by 6 sodium atoms ion. Each sodium atom is similarly surrounded by 6 chlorine ions. Now you will say that what about this? That is one that is present at the terminal end. So this is not the end. There will be much more cubic structure like this, and that will result in the coordination number of 6. So this is structure we got after the X-ray analysis of the ionic compound, and these are arranged in a certain three-dimensional pattern to form a lattice. So this is called as a lattice. Now talking about the ionic compound, they have high melting and boiling point, first of all, because of this strong ionic interactions. Okay, because of this strong ionic interaction, and this is also because ions are tightly packed and closed. Because of the strong ionic interaction, we will tightly packed, and that will result in very high melting and boiling point. What about the solubility? The electrovalent compounds are soluble in solvents like water, which are polar in nature and have a high dielectric constant. Because they are polar, of course they are forming ions, so they must be polar. So they are very easily soluble in water. It is due to the reason that polar solvent interacts with the ions of the crystals, and further the high electric constant of the solvent capacity to weaken the force of attraction, cuts off the force of attraction between these ions. Clear? Next is electrical conductivity. Okay, so since they are ions, so they are very capable of being a very good conductor of electricity in the solution or in the molten state. So this is very important, that they are capable of conducting electricity, but always in their molten or solution state. So this thing should be important, mentioned very clearly. Now, in a solution or molten state, their ions are free to move, right? So why is it so? Why are we taking this in the molten or solution state? Because in that case, they are free to move as the ions are charged and they are attracted towards electrodes. Thus, they act as carriers of electric current. Okay, because if you take the solid form, they are detachable. They cannot be detached in any way. But once you get it in the solution phase or in the molten state, then the ions can move freely and conduct electricity. If you talk about the reaction of the ionic compounds are in fact the reaction between the ion produced in solution. So as the oppositely charged combine quickly, these reactions are therefore quite fast. So means ionic reactions are very fast. Now we have already seen that both of the covalent and ionic bond formation with the help of Lewis dot structure. But this Lewis concept was not enough to explain the bonding. So for that we introduced the VSEPR theory. Okay. So since Lewis concept was unable to explain the shapes of the molecule, so Sedgwick and Powell in 1940 proposed a more simple theory in which it was this interactions were totally based upon the electrostatic interaction, okay, repulsive interaction between the electron pair and the valence shell of the electron. So that is the reason it is called as valence shell electron pair repulsion theory. Okay, and it was further developed and redefined by Nyholm and Gillespie in 1957. So if you talk about the main postulates of valence VSEPR theory, so they are as follows: the shape of the molecule depend upon the number of valence and electron pairs around the central atom. Okay, so whether they're bonded or they're non-bonded, all those electrons should be considered. Next is pair of electron in the valence shell repel one another since their electron clouds are negatively charged. So we know it very well that these pairs of electron will repel each other because they are clouds of negatively charged clouds. Now this pair of electrons tend to occupy such position in space that minimize the repulsion. So what you have to do? You have to simply rearrange this atom such that this repulsion could be minimized by maximizing the distance between them. The valence shell is taken as a sphere. So how do we assume it? So we take valence shell as a sphere with electron pair localizing on the spherical surface at maximum distance from one another. Now a multiple bond is treated as if it is a single bond. So this is again a drawback of this thing, but we will get back to the drawback. So what they did is they took the double bond as single bond, means the bond formation is according to your Lewis dot structure, but the structure, the Lewis dot theory, but the structure is not defined. Okay, so we are now taking those same bonds and trying to redefine the structure. So when two or more resonance structure can represent a molecule, the VSEPR is applicable to any such structure. So we'll talk about this resonance later on. Now, if I talk about the repulsions, so what about the repulsion? So we said that there will be repulsion. So the repulsion is maximum between lone pairs. Okay, so we have seen that we have lone pairs in case of oxygen or in case of nitrogen. We have lone pairs there. Similarly, we have lone pairs here also. So the repulsion between two lone pairs is very much, okay, so it is highest. Then we have repulsion between lone pair and bond pair, and then we have repulsion between bonded pair and bonded pair. So what could be the reason of this? Okay, so what is the reason for this lone pair and bond pair repulsion and all? See, if you talk about the lone pair of electron, then they are not stabilized, right? See, they are just present on one nucleus. Okay, if you remember the lone pair, they are just localized on one nucleus. Therefore, they are not getting that much neutralized because one nucleus will have less positive charge as compared to two nucleus. So those lone pair will be less stabilized, or they will carry more negative charge, and more negative charge means more repulsion. So that is the very direct relation of that. Now if I talk about the bonded pair, so in bonded pair what will happen? Those two electrons that are across the bond, they will be shared upon two nucleuses, and these two nuclei, what they will do, they will kind of stabilize this negative charge in a way. Clear? So since that they will get stabilized, that is the reason they are carrying less negative charge, and therefore their repulsion is in between. So bond pair, lone pair, repulsion is in between, and the least repulsion is when the both of them are bond pair. So with this, I will just stop this lecture. So we have just got an idea about what this valence shell electron pair repulsion theory is. So we will apply it to the molecule, then you will get a more clear picture. Okay. So with this, I end my lecture. Thank you.